Yeah, next talk for today, Marc Bruyere. He wants to introduce you some things about the open source network tester, and will present you some research he did with the NetFPGA 10 gig. So, nice warm welcome for Marc Bruyere.
Hello. Hello, everyone. As he introduced me, then just I'm going to talk about open source network tester based on the NetFPGA 10 gig. Gianni Antiki, who is the guy who coded the part for the capturing part, is not here today, but if you want, you can contact him by this email. I'm going to talk about the NetFPGA 10 gig, NetFPGA, what it is, and there's a different version of this board we've been using for that project. And we're going to go through the architecture and different part of the OSNT, open source network tester, for the generation part and the monitoring part and the hybrid part. We joined the two different projects in one a bit file for the FPGA. And a framework we've been using for research parts and one other use case I'm going to show that we've been using for testing FNS switches. Computer networking is obviously something we use every time, every day, and need to be tested. We can test by software to software, but when you want to test high performance switches, you need hardware. You need a hardware who is able to keep up in terms of line rate for testing hardware to hardware environment for network. Then there is a lot of data you need to generate, and it's only through FPGA and or network processor that with FPGA you get a better timing than you cannot get on even on NPU, network processor unit. Well, one thing about networking is there is a lot of protocols. There is a lot of different standards, and if we talk about low levels, OSI levels, then we talk about a lot of different protocols who are actually need to be implemented. And there's standard groups, IEEE, there are IFC from EATF and so on. If you need to follow this, is very difficult, and every time need to be implemented by a vendor company, then this is difficult. And that's why it come up with a teaching platform, the NetFPGA. Then you're able to do your own implementations. The NetFPGA is been designed at Stanford for the first generation with the help on the 10 gig with Cambridge University in UK. There's different applications. Then you can do your own NIC card and hardware accelerated Linux router. Then you use the FPGA to do the forwarding part and being controlled by the whole system where the NetFPGA is. And the reference router, traffic generation, open flow switches, and much more projects. Is around, if you go on the netfpga.org website, you will find about 30 different projects with all open source. Then you get in 2007, that was the NetFPGA 1 gig board. It was 4 1 gig with Virtex with different memories, and the Spartan was taking care of the PCI connections. Then the project NetFPGA is for different things. Then we get obviously the board itself, the tools and the reference design, then students and hackers can use to do their own project. And the contributed project, that's the one we can find on the netfpga.org website and the community itself. Then after the 1 gig version, it's been designed the 10 gig to be able, obviously, to follow with the performances we get on the Ethernet switches today. It's 4 10 gig, and it's state-of-the-art technology at that time. It's been designed a few years ago already. And then we go 4 SFP cages, when you can place different SFP plus transceivers. And you can have direct attached copper cable, or you can plug different optical fiber transceivers for 10 gig or 1 gig. On the board itself, then we have a SRAM, or actually for placing the different storing routing tables or CAM or different information you want to have on very high-speed connections. And there's a DRAM also for being able to buffer some part of the things you want to tweak. And the PCI Express connectors is the endpoint, and the difference of the 1 gig is directly on the Virtex itself. And you have an extension slot will allow to get the different GTX transceivers. Then to extend the connections of the FPGA itself, if you want to use the different port and connect out of the board different channel for being able to get in and out without passing through the PCI is possible through the extension slot. It's all optimized, obviously, for being able to keep up on 40 gig, 4 times 10 gig. Then we're not losing any packets with this design. And what is about is, obviously, when we talk about the different protocols implementations today, there is different vendors, all commercial. They sell their licenses, and it's pretty expensive. And obviously, they have different functionality for different type of interfaces in terms of networks. We focus on the main one used is Ethernet. But we have the same capacity of those vendors in terms of hardware. And the main differences for us is being able to put your hands onto the code, and it costs a lot if you want to go for a commercial implementation. Just to get a couple of 10 gig port, it will cost you $25,000 box easily, just to get the license on the software to need to run the hardware part on the FPGA you have on the XIA, for example, implementation for 2 port 10 gig. Those equipment are very dedicated for testing clusters, for example, when you want to run high-performance testing onto a cluster of server, or more precisely to test, if you want to test just a new design of your new switch Ethernet, then you need to get those capacity. It's a very small market and a long development cycle for those guys. But then it come up for us to why not try to do on the NetFPGA OSNT, open source network tester, to be able to do the same things that XDI is doing, for example, with a reference. Then to have a low-cost and open source approach. When we talk about open source, we talk also open source on the PCB itself. Then you can have access when you register on the GitHub we have. And as is dedicated for research and teaching community, it's also used in different universities, not only Stanford and Cambridge, but a lot of us, for teaching how to make hardware routing or switch based equipment. Then you need a PCI like this. We started last year in June the project, and the kickoff was in middle of June last year. Then we designed at that time on paper what we wanted to do, and we had to work on the generation part and the monitoring part, all separated. Shabbat was from Georgia Tech. He was developing the generation part, and the monitoring part was being done by Gianni, and Ilong was doing the interfaces and so on. I was doing more the testing and following the project. And Adam Covington was the guy from Stanford who helped us to interface everything as well. Then architecture part, and just mentioned the different two parts of the traffic generation part. The traffic generation part is being able to run on line rate on the 10 gig port, and obviously to test, as mentioned, for the small market and do the same thing. The monitoring part is being able to, on design, to capture packets, timestamp or filter some packets out of the pipe of 10 gig, and cut or hash the packets. The hybrid is actually the join of the two projects. Then we're going to look into the details after this. And our approach, we try and design to be able to bring more modules after this and be able to implement OSNT on different platforms and not only on the NetFPGA, because the software part we have on the host system where the PCI and NetFPGA is plugged could be used on different other platforms. Then we're going to look into the generation part. On the first stage of the design, we decided to do a pickup replay. And also, in the same time, try to, obviously, in the code we implemented on the traffic generation part to get micro engines to be able to run traffic models, and different headers being implemented to be able to generate directly from the FPGA the traffic. The pickup replay was the easiest way, we thought at the beginning. Obviously, we had some problems to implement it, but now it's running. And on the different capacity we have is not only what packets we need to generate, but we need to also the packet size and the inter-packet delay for tracking the data rate we want to generate, because we don't want all the time to get the line rate 100% of 10 gig. We may want different interframe gap, a slower packet rate. The architecture, then if you look into details, then the gray boxes represent the ongoing work, and this part, the timestamping on the packet out generated, is now implemented. That wasn't the case when we made that slide. Then the delay module and the rate limiters are guaranteed output and that the user wants. And the 25 SRAM is used to store the packet. Then on the we're talking here for the pickup replay. Then obviously the pickup we use when we talk about pickup is is the file then we get from a TCP dump or Wireshark. Then you can reuse it. You just capture traffic, and you can reuse it. Or obviously you can get that pickup as well from the OSNT itself and replay the traffic you just capture. And is the amount of data you're able to regenerate. Then you will loop around the 27 megabyte of SRAM. Then the micro engines we're still working on is they're here. Then obviously is the interface to be able to say exactly you want, for example, a UDP packet with this IP, just generate from here and not like we do today, a pickup replay engine will be generated directly by the micro engines. And then it could be different type of protocols in the same time going into the pipeline out. And it's ongoing. Statistics collectors, it's just obviously how many packets being sent and what type of packets and information like this. The time stamping on out, then there's it helps obviously when you want to test the latency along a data path when you're sending a packet with a timestamp in. You know when it's been sent, then you can capture the same packets and obviously compare the two timestamp. And to be sure you get the right packet, because there's a lot of packets going out in the same time, you can compare by signature. Then we had to decide the way we're going to do the timestamping. It was very important, and that's one of the reasons I joined that project as part of my PhD, to measure latency in an open flow environment. There is two ways to think of the implementation. Or you use a free run counter directly, driven by the clock itself. But the clock of a board like this will drift when you need that nanoseconds precision. Then we decided to use the direct digital synthesis, who is actually who needs a GPS synchronizations or whatever other synchronizations, or one PPS today. 1 packet per second, high precisions all the time. And he slowed down a little bit the counter, or he accelerated just to obviously keep the synchronizations and avoid the drift we have based on temperature change we have on the clock and some other things like this may happen. Then we've done some measure on the NetFPGA a few time back. And we've seen that even the drift we have here on that clock was a little bit worse than a normal swatch. That's why we implemented DDS. And the interface, we use Python, and it's pretty simple. It's all we need, obviously, to be able to generate traffic. Then we select per pore, the different, the 4 pore we have, the pickup we want to run, and the number of time, and the different information where it's placed on the ESRAM, just for debugging. And the rate limiter side, just obviously what the speed you want to have of these interfaces, and you call also for inter-packet delay. If you want to use the timestamp, where is the time of the pickup itself, then to generate exactly the timing that the capturing traffic you had will be replayed, or you can do your own timing, will be obviously the same because we have one input only for delay register. And that's almost it, just to be able for the first functions, for the pickup replay, to be able to replay all the time the same traffic, which could be generated by different interfaces or a live traffic. During the testing, then we could on one pore at the just beginning against an XCR to measure the traffic generated. But we implemented for the second port because we need to integrate different blocks of RAMs allocated into SRAM. Then as is today, then we are really able to run full line rate on 2 ports. When you get a third port, it will be a little bit less than 30 gig as expected. And obviously when you get 4, it gets less as well. Then we need to implement more blocks into the EHSM. That's an effort we are doing today to be able to run 40 gig line rate. The 96-bit is the interframe gap we cannot change because we use the McPhee was generated the end of the flow, and the only things we can increase, obviously, the interframe gap. We cannot go below 96-bit of space between 2 packets when we send the packets on the fiber or the copper. That's one difference we have on the commercial implementation. They can go smaller interframe gap. Then on the monitoring part, here obviously is to be able to capture as much as possible on the port. Then we can choose by filter rules. We have 5 tuples with classically source and destination, MAC address, and IP, and the TCP port, UDP or TCP port. That's the classical 5 tuples. Then you have to think that this is very easy here to implement other filtering rules, because we can just modify the code to be able to go on even on payloads if you want to match on a particular pattern on the payload. Then we worked on to getting on the high precisions on the timestamping, because it's a part of the reason of OSNT. And the timestamping we're going to see on the architecture, where it's done and how it's done. Then the different statistics we get, we're going to look into the interfaces. There's some other statistics we can get from the card, but on the GUI we made with just the simple ones. Then we received on the 4-port 10 gig here, just on the top, and right after we received the packets, and they are check, because we have on our Ethernet header, we have at the end of the Ethernet header, we have a CRC to check if the packet is it's a good packet. When this is done at that level, we just timestamp, and this timestamp is actually next to the normal pipe where the packets get in, to avoid any effect of buffering we can get, to be able to timestamp very high precisions. When the packet get in, it really timestamp it. Then we have the statistics collectors. We give us different information to the Linux box. The header extractions and TCAM and decision modules, where we do the filtering stage, and packet FIFO to send out. And obviously the decision module say, okay, based on the filter, have just cut that packet and send on the PCI to the host system, and do a hash if necessary. Then one thing, so obviously we work on one protocol as .1Q to be able to get the VLAN numbers as well, because in networking today, VLANs are spread a lot. Then obviously, yeah, just the same information. We go to the GUI itself. The different port, the packet counter, the VLAN packet counter, if it's an IP packet, UDP or TCP, and the packet rates or bit rates. Here are the filter rules. Then everything is need to be loaded and modified through the console by a file. was loaded separately from the GUI. And the cutter and timer, then the timer is when the application's been run, you can reset it just for information. And the cut length, if you implemented cut, you need to cut just a few bytes from the beginning of the packet. You want the first 128 byte of a packet, then it will, for example, show here, and a console log to give you the different actions you made on the GUI. This application, where the GUI is connected, is C-based. And we generate, based on the filter, normal pickup or new generation pickup. There's a slight difference, especially for new generations. It allows nanoseconds by default on the pickup NG. Then what we've done to be able to use the normal pickup, the default pickup file, we patched to get nanosecond precisions into the pickup. And you're also able to use a CLI command base to be able to script outside of the GUI, the application. Then we moved a different project into the hybrid, was actually the generation and the monitoring were bring together into the FPGA. It took us quite some time to be able to do it. Not on terms of effort, but on calculating for the routing to be able to get the two projects on the FPGA. And this approach led us to get different pipeline if you want other pipeline in the same time to be implemented. And now let's use it. When we have a switch with 48 10 gig port, for example, then it's difficult to get a big tester with itself 48 10 gig port to connect directly in all the ports to each others. Then what we can do with OSNT or other is if you want to just test the performance of all the ports, use the snack test. The snack test, you configure 2 ports in the same VLAN, and then you generate a layer 2 with one MAC address, the same one, and it will go through the different ports one by one, getting in and out along the cabling you're gonna place to test the 48 10 gig port. But for you're just using one port to generate the traffic, another one to receive it, and in opposite way as well. Then you can test on full duplex with only 2 port 10 gig, whatever number of port you have on the switch you want to test. This is pretty useful if you want to test on layer 2 only switches. If you want to test for routing layer 3, then you need VRF. You need different another approach to configure, prepare the different port. One project we used OSNT is in software-defined networking. Is change in the networking today is to separate the control plane with taking care of controlling the network, who is connected to which subnet you can reach, like OSPF, BGP, the different routing protocols, for example, are actually getting separated, and that control is getting out from the closed boxes, from the switch header router we have today. And OpenFlow is one protocol who we're able to control the OpenFlow switches while doing the forwarding and maintaining the data plane, the data path. Then we use OSNT to be able to test new OpenFlow implementation we have today. We change with the OpenFlow request on the switch to say, for example, just change a flow and how much time. Then we measure the time it will get the switch to do that actions. In the OpenFlow implementation and design we have today, this information is very critical when you have a lot of flow who need to be modified. And then obviously we have different testing scenarios we use to be able to see the limitations of next generation OpenFlow switches using the OSNT. All the guys who've been participating to the project from between Stanford, Cambridge, Georgia Tech, and other universities. And I invite you to join and get a look into the OSNT.org. There is a video who show you how running is the project, and you can join the GitHub and the different mailing list. Thanks.
Okay, we have some time for questions now. Any questions in the audience?
Hi. I'm more curious about how the timestamping was implemented. Was it just a variable speed counter with a phase detector on the one PPS input, or was it done differently?
Just by DDS. It's the counter. Just when you saw the time reference we had on a GUI, then you can reset it. Then it will use that counter. Then it's exactly showing the counter itself. And obviously 6.25 nanoseconds is the any increment in the counter itself on the FPGA represents 6.25 nanoseconds. Then DDS try to keep obviously the reference time on UTC time using the GPS to correlate with that counter, to accelerate it or slow it down to stay around the GPS input.
Any more questions? Okay, fine. Thanks, Marc, for your interesting talk, and a happy applaud for Marc.
Thank you.